So we just talked about classifying critical numbers using the first derivative test, right? And so we're looking at critical numbers, taking the derivative and making a sign chart to see how that increasing and decreasing behavior changes potentially at a critical number, and classifying the critical numbers based on the behavior of the function. Okay, so now we're going to take this in a different direction. If we didn't want to do a second or a first derivative test, there is a second derivative test that in some cases may be easier. In other cases, you may just say no and you want to stick with the first derivative. But remember, when we're working with the second derivative, that tells us about concavity of the function. So if the second derivative is positive, that means that we have the function being concave up on that interval. If it's less than 0, that means it's concave down. And then if the second derivative is 0, that just means that it may have an inflection point. So just make sure to have that correction. I say may have because we actually need to verify that the function changes concavity at that point. All right, second derivative test, what does it say? It says, okay, we have to have a continuous second derivative and we have to find our critical numbers. So C is just a critical number. That's all that language says. Okay, so then if we look at the second derivative and evaluate it at our critical numbers, okay, if that evaluation yields a positive number, then we actually end up with a local minimum. Okay, a little counterintuitive, right? And then if we take the second derivative, evaluate it at our critical number, and it's negative, then it's a local maximum. Okay. Now, for me, this is always very hard for me to remember, just because it's this opposite behavior of what you think. And so I remember the second derivative test with my friends Maxi and Minnie. Okay. So here's how I remember this. So there's Maxi and then there's Minnie. Okay, and I'm just need to set this up. So I'm going to set, here's f double prime, f prime, and f. Okay, so what I know about both of these is that if I have a local max, right, it's going to look something the function is going to look something like this. Okay, and there's my maximum value, right? At that maximum value, the derivative is 0, and the second derivative is going to be negative because it's concave down. Okay, the function looks concave down. So there's my friend Maxi. Okay, and so you can imagine here's a little face. It's a nice little emoticon or emoji, whatever you call these things now. Okay, and then Minnie, well, Minnie, if you have a minimum, it's going to look like this, right? And then at that point, the derivative is 0, but then the entire function, as you look at it, is concave up, so the second derivative should be positive. And there we have Minnie. So we have happy Minnie and unhappy Maxi, if you want to think about it that way. Okay, so now we're going to look at an example where we use the second derivative test. And we've already classified the extreme values here, but we're just going to do it in a different way. Okay, so I'm going to run through this lightning fast. We look at the first derivative, right, and we got 6x squared minus 6x minus 12. Okay, set it equal to 0, and we ended up getting x is negative 1 and positive 2. Okay, negative 1 and positive 2. So those are my critical numbers. Okay, now according to the second derivative test, okay, I'm going to find this, f of x, I should say, and so I get 12x minus 6. Okay, now I evaluate my second derivative at each of these values. Okay, when I put in negative 1, I get, negative 18, which is less than 0, so that automatically means, okay, so my second derivative is negative, right? So then I'm in the maxi case, so that means I have a local max at x is equal to minus 1. Okay, it's consistent with what we saw before. Second derivative at 2, this is going to be what, 30 or 24 minus 6, so that's a positive 18, which is greater than 0, so then I'm in the case where my second derivative is positive, right? So that's the mini case, so that means I have a local min at x is equal to 2. Okay, so same sort of thing as what we got before, just presented in a different way. So in total, all right, so we have the first and second derivative tests to classify local extrema. Okay, if we're in the case where so there's first derivative test. If we're in the case where we want to classify the absolute extreme values, then that's a bit of a trickier situation. We either need to look at the graph, or if we are on a closed interval, that's when we can use the closed interval method. But that only applies when you're on a closed interval. Okay, if you're on the domain of all real numbers, this does not apply. Okay, so just maybe make a little cheat sheet of all these different methods you can use to classify, or to find and classify extreme values before we go on to the next examples.